Welcome to Sage Step Shorts. Some of you may be familiar with the Sage Step project, which is a long-term fuel reduction treatment experiment with 20 sites across the Great Basin. We now have at least 10 years of post-treatment data and are putting the results in a special issue of the journal EcoSphere. Today, Dr. Bruce Roundy is here to talk about his recent paper. Welcome, Bruce. Tell me, what makes your study unique considering all the existing research on pinyon juniper?
Okay, well, the Sage Step Woodland experiment was set up to test the effects of tree expansion as well as tree reduction and fuel reduction on understory vegetation response. So I'll show a few graphics to kind of talk about how our study fits into the overall study. So we all know as pinyon and juniper trees expand into sagebrush communities, the understory vegetation starts to change. And we've identified, for management purposes, three kind of phases that occur where the trees are first entering in, as you see over here on the left of your screen, then kind of an intermediate stage where the understory and the trees share cover, and then over to the right, phase three, a dominant, where the trees are dominant and you see very little understory. We also know that when you go and kill the trees, either by fire or mechanical means or shredding, whatever you do, you see an understory response. And this can be good or bad. On this site, you see blue bunch wheatgrass doing really well after the trees are dead, but also you see some cheatgrass in there. And we were curious about why we see this difference, why we get such a response when we take out the trees. And we were really interested in, does this expansion have some effect on the environment that the understory is experiencing? And as the trees are reduced at these different phases, does it make a difference in the vegetation? And why would that be? The management treatments that we implemented were typical treatments: prescribed fire, chainsaw cutting, and shredding, mechanical means. And we compared this with no treatment at all. To understand our study, you kind of have to review the hydrology in the Great Basin. And our climate in the Great Basin are cool, wet winters, followed by warm, dry summers. And this results in a short period of time in the spring, typically between March and June sometime, where soil moisture is available for plant growth. And we get precipitation in the winter and in the fall and a little bit in the summer, but we don't get a lot of plant growth out of that compared to the spring. And here's a generalized diagram of where the precipitation goes in a pinyon juniper community, and this varies greatly by site. But a lot of that precipitation can be intercepted by pinyon and juniper trees. And what isn't intercepted goes into the ground and then evaporates out, transpires through the plants or directly from the soil. And you see that's a large component here. Now, the soil water availability and its importance depends on the depth in a sagebrush community. For example, the upper 30 or 40 centimeters are what we call the growth pool, because that's where the nitrogen is. And when soil water is available and temperatures are warm enough and there's nitrogen there, that's where you get your maximum plant growth, typically in the spring. And the roots are taking that from the upper 30 to 40 centimeters. So we call that the growth pool. The maintenance pool is deeper than that, can be even a few meters deep, especially for sagebrush roots, but that doesn't have a lot of nitrogen in it, so not a lot of growth comes from having roots that deep. However, soil water availability is important in the maintenance pool because it carries the shrubs through the dry summer. So what we wanted to do was measure soil moisture on all of these phases of expansion, both without any treatment and with treatment. And so we ended up putting out over 100 soil moisture stations to do that. And we put them on at least 10 sites and measured, for the purposes of this paper, 12 to 13 years since treatment, depending on the site. So we have a lot of data, a huge amount of data. And what did we find out? So over on your left, this is the untreated plots. And what we're graphing here are the number of wet days in spring. And spring is from March through June every year. And these bar graphs come from averages over up to 12 years after treatment. And what we find is on the untreated, as you progress with more expansion, you get fewer days of soil water availability in the growth pool and also in the maintenance pool. Now, it doesn't decrease greatly, but it does decrease. Why would it decrease? Well, maybe more interception as the tree canopies increase, maybe more soil water use by the trees as they get bigger and their root systems are big. Probably both things happen. So we know that as the trees increase and expand, they reduce the soil water available for the understory species. And that's why you typically walk around in a phase 3 or phase 2 to 3 pinyon juniper stand, you can see dead sagebrush, bitterbrush, and other shrubs, and limited grass growth. So we did find out that the trees are reducing soil water availability. Okay, over on the right side here in this graph, we're looking at additional wet days or additional days when soil water is available in spring from March through June. And this is averaged over 12 to 13 years across all our sites. And it's for each of the different phases. And what you see on average is when you remove the trees, either by burning or mechanical means, you get another 2 weeks of soil water availability in the growth pool at phase 2 and phase 3, if you remove the trees at those phases, and even longer in the maintenance pool. So that's soil water days, or days of available water, that those plants in the understory can use that they wouldn't use or wouldn't have available to them if the trees were there. So we see now that in a resource limited environment, we're getting resources given to another component in the plant community once you take out the trees. We also found, and this is additional wet days in spring between March and June, that it's not the same every year, and soil water availability varies greatly, as does precipitation on an annual basis in the Great Basin. So on a wetter year, you don't get as many additional wet days from tree reduction as you do in a drier year. In a drier year, you could get up to 3 to 4 weeks of more soil moisture availability, having reduced the trees.
What do you think the take-home message is here? How can managers use this information?
So there's really 3 kind of things that are important. One of those is when you have wildfire or you reduce the trees at phase 3, you get the biggest bonus of soil moisture. And that's because the trees are gone and there was very little understory left to use that soil moisture. Right. That can be both a bonus and a risk. One of the bonus is if you have plants that can respond, and we've shown in our studies that the perennial grasses respond quite well and increase their cover very well, even at phase 3 on some of our sites. But you can also get in invasive annuals like cheatgrass, which is what you don't want. So one thing is, I guess we add this study's evidence to the studies of our other colleagues that you should probably treat at earlier phases. If you want to have desirable plants, use that available soil moisture that's freed up when you take the trees out. Another thing would be that if you have wildfire or you have to treat at phase 3 and you have wildfire in phase 3, you're going to have resources made available. And so you should probably do revegetation under those circumstances so that you can reduce the tendency of cheatgrass to come in and dominate the site. Why was the soil moisture availability information useful? Well, we've shown that 12 to 13 years after treatment, you still have a bonus of soil moisture compared to an untreated site. And either desirable or undesirable or a mixture of both, plants will use that. So we're showing that resources are made available for plant succession. And this can be useful for land managers because your response to tree reduction doesn't happen right away. It's going to happen over a long period of time. And in the Sage Step project, we'll continue to monitor what's happening. We hope the perennial grasses and shrubs will dominate and the cheatgrass will not dominate, but we have to monitor for many years to see that because that soil moisture bonus continues for many years.
Oh, that's really interesting. And so what are the next big questions that need to be asked in this research?
Well, one of the things that might be interesting is just to see how long this bonus of soil moisture does occur. And little trees will start coming back. They're already coming back, especially on the mechanical plots. Will the cheatgrass that's there and it has been increasing, will it decrease over time? And somebody will use that soil moisture. Also, there's probably an interest with global climate change, how soil moisture varies over the years, and can it be predicted from aerial imagery and other types of remote sensing, and can it be related to our on-the-ground measurements? Those are some of the things that could be studied in the future.
Thank you so much, Bruce. You can find this paper and our other EcoSphere special issue papers in the link below this video.